star-star connection, which is also called Y-Y connection. And here the assumption is on primary side HV winding and on secondary side LV winding. And the important point that we must keep in mind here is that in vector group symbol, the first character always represents the HV side winding connection and second character always represents the LV side winding connection, irrespective of what is primary and what is secondary. And here we took an example of a transformer which is having HV winding on primary side and LV winding on secondary side. So consider bank of 3 single phase transformers and let's give the dot notations on both primary side and secondary side. And here we are considering the case of star-star connection, which means primary winding is star connected and secondary winding is also star connected. So first let's connect the primary winding in star. So to get star connection, we must join the common terminals and take the connections on other ends of the winding. So to get star connection, we must join the common terminals and take the connections on other ends of the winding. Means if suppose this is the one winding which is having terminals A1 and A2, and let us suppose this is the other winding which is having terminals B1 and B2, and let us suppose this is the third winding which is having terminals C1 and C2. So to get the star connection, we must join the common terminals and take the connections on other side. Means let us consider the common ends be A1, B1 and C1. So then if this is A2 and let this be the B2 and let this be the C2. So we consider the common ends as A1, B1 and C1. So join these common ends and take the connections from the other ends of the coil. So this is how we can obtain the star connection. And the other way of obtaining star connection means consider the common ends as A2, B2 and C2 and take the connections from A1, B1 and C1. So this is how star connection is obtained. From this star-star connection, we are going to see how to get the star-star connection and then the phasor diagram and the vector group and phase voltage ratio, line voltage ratio, and finally its advantages, disadvantages and applications. Now let's obtain the star connection on primary side and then star connection on secondary side. First we need to assign the notations, and it is discussed that the dot ends are given the notations A2, B2 and C2 on primary side. As this is HV winding, we are giving the capital letters, okay, and on secondary side the dotted ends are small a2, small b2 and small c2, because LV side terminals notations are given in smaller case. On primary side, as this is the starting end, so finishing end will be A1, and to this B coil this is B2 starting end and finishing end is B1, and to this coil C2 is the starting end and C1 is the finishing end. And now coming to the LV side, that is secondary side, finishing ends A1 and B1 and C1, and it is discussed that to obtain the star connection we must join the common terminals. So here the common terminals could be starting ends or could be finishing ends, and here we are considering the common ends as A1, B1 and C1. So let's join the common ends A1, B1 and C1 together. And coming to the secondary side, let's join the common ends A1, B1 and C1. And now on primary side, let's take the connections from the other ends, that is A2, B2 and C2. A2, B2 and C2 are the dotted end terminals. And similarly on secondary side, let's take the connections from A2, B2 and C2. So this is how we are obtaining the star-star connection. And now to draw the phasor diagram, let's arrange these windings in horizontal fashion. Let these three be the HV side windings and let these three be the LV side windings. Okay, and let the dotted ends be these, and as 3 are considered as HV winding, so let's give the notations. So this will be A2, B2 and C2, and these will be A1, B1 and C1. And now coming to secondary side, that is LV side, let's give the notations. So small a2, small b2 and small c2, and these ends will be small a1, small b1 and small c1. Now observe that to obtain star connection, what we did? We joined the common end terminals, that is we joined the finishing end of coils. So the finishing ends of coils are a1, b1 and c1. So let's join these a1, b1 and c1 together. And we are taking connections from A2, B2 and C2. That is, we are taking the connections from dotted end terminals. So this is how we obtain the star connection on primary side. Now let's obtain the star connection on secondary side. That is, let's obtain the star connection on LV winding. Here we took the common end terminals as finishing ends. Let's join these common end terminals together. That is A1, B1 and C1. And we are taking the connections from dot end terminals. That is small a2, small b2 and small c2. So this is how we arranged the star-star connection in horizontal fashion. Now let's draw the phasor diagram for primary winding, that is HV winding. Let's consider the VA phase phasor like this. Now we need to decide the terminals of VA phasor, and here we are taking the connection from dotted end terminals, that is from A2. So arrow will point towards A2. Obviously this will be the A1. And now we need to draw the VB phasor and VC phasor. So in three-phase system, it is known that if VA is taken as reference for ABC phase sequence, VB will be at an angle minus 120 degrees and VC will be at an angle minus 240 degrees. Okay, so to VA phasor at an angle minus 120 degrees, there will be VB phasor, and to this VA phasor in clockwise direction, because minus 120 degrees, so in clockwise direction up to 120 degrees there will be VB phasor, and here we need to decide the terminals. So here in winding connection, VB is having B1 and B2 as terminal, and we are taking the connection from B2, means arrow will point towards B2. So obviously this will be B1. And similarly now let's obtain the VC phasor. So VC phasor will be at an angle minus 240 degrees with respect to VA. So in clockwise direction from VA phasor at an angle minus 240 degrees, there will be VC phasor. And now we need to decide the VC phasor terminals. So here we took the connection from C2, means arrow will point towards C2. Obviously this will be the C1. So this is how to obtain the star connection phasor diagram. Now let's draw the phasor diagram for secondary side star connected winding. And it is studied that the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. So this is secondary side VA phasor drawn parallel to primary side VA phasor. Now the next step is to decide the direction of secondary side VA phasor, and observe that in winding connection, now on primary side winding connections are took on the dot end terminals, and similarly on secondary side winding connections are took on dot end terminals. So as here the winding connections are took on dot end, and on this side the winding connections are took on dot end, means the direction of secondary side VA phasor will be same to that of the primary side phasor. And now we need to decide the terminals of secondary side VA phasor. So terminals of VA is A1 and A2, and here we took the connection from A2, means arrow points towards A2 because connection is took from A2. So this will be A1 terminal. And now let's draw the VB phasor. So first let's draw the phasor parallel to primary side VB phasor, and now we need to decide the direction of secondary side VB phasor. So observe the winding connections on primary side and secondary side. On primary side and secondary side we took the connections from dot and terminals, means here the secondary side phasor direction will be same to that of the primary side phasor direction. So VB will be in same direction. And now we need to decide the terminals of VB phasor. So VB is having terminals B1 and B2, and connection is took from B2, means arrow will point towards B2. So this end will be P1. Now coming to this VA phasor, okay, observe in winding connection A1 is joined to B1, means to A1 there will be B1 connection, means this phasor will be like this. So this is B2. And now let's draw the VC phasor. So secondary side VC phasor will be parallel to primary side VC phasor. So primary side VC phasor is like this, means secondary side VC phasor will be also like this. And now we need to decide the direction. So observe in winding connections that here we took the connections from dot ends on both primary side and secondary side, means the secondary side phasor will be in same direction as that of the primary side VC phasor. And now observe in winding connection that here we took the connections from dot and terminals on both primary side and secondary side, means the secondary side VC phasor direction will be same to that of primary side VC phasor. So direction will be same like this. And now we need to decide the terminals of VC phasor. So observe in secondary side that we took the connection from C2 terminal, means arrow will point towards C2. So this will be C1. And now observe in winding connection that to A1 B1 C1 is connected, means C1 will be here. So draw this phasor like this. This is C2 and this will be the VC phasor. So this is how the phasor diagram for secondary side is obtained. And now we need to identify the vector group symbol for this type of star-star connection. In clock notation, the HV winding phase to neutral voltage is taken as reference and is represented with minutes needle and is always shown pointing towards 12, because phase to neutral voltage of HV winding is taken as reference. So always the minutes needle is shown pointing towards 12, and secondary side phase to neutral voltage is represented with hours needle. So let's first superimpose this diagram on this diagram and observe the primary side phase to neutral voltage and secondary side phase to neutral voltage. So if you observe that both the primary side phase to neutral voltage and the secondary side phase to neutral voltage will look like superimposed on each other, and as the secondary side phasor is represented with hours needle, so this is how it is drawn. And let's observe this in clock. So if you observe this in clock, it will represent 0 clock hours, and the phase angle difference between the minutes needle and hours needle will represent the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage. Now let's obtain the vector group symbol. So in vector group symbol, first character is in capital letters and that will indicate the HV winding connection. So observe that HV winding is star connected. So to represent that, the first character is given Y, capital Y, and the second character is in smaller case and that will represent the LV winding connection. So as here the LV winding connection is star, so here small y is taken to represent that. And now the third position is the numerical from clock. So here the clock hour is 0. So the third numerical is 0, or you can take as 12. And this 0 clock hour means the phase angle difference between the minutes needle and hours needle is 0. Therefore, the LV winding phase to neutral voltage is having a phase displacement of 0 degrees with respect to the HV winding phase to neutral voltage for this type of connection. And the other way of obtaining the star-star connection is keep the primary side winding connection as it is. And now coming to the secondary side, instead of joining the non-dot-end terminals A1, B1 and C1, here we are joining the dot-end terminals A2, B2, C2 and taking the connection from A1, B1 and C1. That is joining the dot-end terminals and taking the connection from non-dot ends, small a1, small b1 and small c1. The phasor diagram for HV winding connection is same as that of the previous case. And now let's draw the phasor diagram for LV side winding connection. So LV side phasors are drawn parallel to primary side phasors. So first let's draw the secondary side VA phasor parallel to primary side VA phasor like this. And now we need to decide the direction of secondary side VA phasor. So observe that in primary side the connections are took from dot end terminals, and coming to secondary side connections are took from non-dot ends. Means the secondary side phasor will be in opposite direction to the primary side phasor. So here, as on primary side the phasor is pointing upwards, means here on secondary side phasor will be pointing towards down. So this is the secondary side VA phasor. And now we need to decide the terminals. So A1 and A2. So as the connection is took from A1, means arrow will point towards A1. So this will be the A2 terminal. Now let's draw the secondary side VB phasor. So first let's draw the secondary side VB phasor parallel to primary side VB phasor. And now we need to decide the direction. So observe in primary side that winding connections are took from dot ends, and on secondary side winding connections are took from non-dot ends. Means the secondary side VB phasor direction will be opposite to primary side VB phasor. So as this is towards this direction, so secondary side VB phasor will be towards this direction. And now we need to decide the terminals. As the connection is took from B1 terminal, so arrow points towards B1 and this will be the B2. And observe in the secondary side winding connection that A2 and B2 are joined together. Means here in phasor diagram to A2 there will be B2. So this phasor will be drawn like this. This is B1. So this is VB phasor. And now let's draw the secondary side VC phasor. So secondary side VC phasor first is drawn parallel to the primary side VC phasor. So drawing VC phasor parallel to primary side VC phasor. And now we need to decide the direction. So on primary side connection is took from dot end, and on secondary side connection is took from non-dot end. Means the secondary side VC phasor direction will be opposite to primary side VC phasor. So like this. And now we need to decide the terminals. So here the output is taken from non-dot end, means arrow points towards C1 and this will be C2. And now observe that in winding connection to A2 and B2, C2 is connected, means here C2 will be here. So draw this phasor like this. So this will be C1. So this is how the phasor diagram for secondary side star connected winding obtained. And to these common connections you can give the common notation N. So for HV winding phasor diagram capital N, and for LV winding phasor diagram the common point is given small n. And now let's obtain the vector group symbol. And it is known that the first character in vector group symbol is in capital letter and it will indicate the HV winding connection. So here we took this as HV winding. So the HV winding connection is star, and so it is represented with capital Y. And in vector group the second character is in smaller case and that will indicate the LV winding connection. So here it is star. So in small letter Y it is represented like this. And the third position is a numerical which is given from clock notation and which will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage. And from this phasor diagrams, the HV winding phase to neutral voltage is taken as reference and it is represented with minutes needle in clock. So if this is the clock and minutes needle is always shown pointing towards 12 because HV winding voltage is represented with minutes needle and it is taken as reference. So minutes handle will be always at this position of 12. And now from the LV winding phasor diagram, the phase to neutral voltage is represented with hours needle. And now if you superimpose the LV winding phasor diagram on HV winding phasor diagram, the HV winding phase to neutral voltage will look like this and LV winding phase to neutral voltage will look like this. Means in clock this is hours needle pointing towards 6. Therefore from clock notation we got 6. Therefore from clock notation as it is 6 means in vector group symbol the third numerical is 6, which will indicate the LV winding phase to neutral voltage phase displacement, and that phase displacement is the phase angle difference between minutes needle and hours needle. So here the phase difference between minutes needle and hours needle is 180 degrees. So these are the two possible connections of star-star connection, from which we got the 0 degrees phase displacement with one type of winding connection and 180 degrees phase displacement with this type of connection. Now let's know the phase voltage ratio of star-star connection, which is same to that of turns ratio of single phase transformer, and that can be taken as equal to N2 by N1, where N2 represents the secondary side turns and NV represents the primary side turns. And coming to line voltage ratio, and it can be taken as equal to turns ratio or not, that depends on the type of connection employed in three-phase transformer. Now let's find out the line voltage ratio. Let capital V2 be the secondary line voltage and capital V1 be the primary side line voltage and small v2 be secondary side phase voltage and small v1 be primary side phase voltage. So here turns ratio K can be taken as equal to small v2 by small v1. So line voltage ratio is given by the secondary side line voltage V2 by primary side line voltage V1. And observe that the secondary side is a star connection and the voltage relation between the line voltage and phase voltage is V2, which is a line voltage on secondary side, which is equal to root 3 times the secondary side phase voltage. Means V2 is equal to root 3 times small v2. And observe in primary side, so it is also star connection. So the relation between line voltage and phase voltage in primary side is primary side line voltage V1 is equal to root 3 times the primary side phase voltage. Now replace this capital V2 and capital V1 in line voltage ratio with phase voltage relations. So it can be taken as equal to root 3 times V2 divided by root 3 times V1. So root 3 cancels and which can be taken as equal to small v2 by small v1, and that can be taken as equal to K because here K is equal to small v2 by small v1. So here are the advantages of star-star connection. The first advantage is no phase displacement, that is we can have 0 degrees phase displacement with star-star connection. And if neutral connection is taken, it can handle large unbalanced load. So if neutral connection is there, then the star-star connection can be used for large unbalanced loads. And if the neutral connection is taken, then it can be used for supplying the three-phase 4-wire system. And with neutral connection, output is sinusoidal. Output is sinusoidal means we know that in phases there will be triple harmonics, and because of which we are getting non-sinusoidal output. So to get sinusoidal output in phases, the triple harmonics must be reduced to 0. So how can we reduce the triple harmonics to 0? Means by providing path to those triple harmonics. So in star connection, that path is provided by the neutral connection like this. So the triple harmonics which are induced in the phases take the path through this connection like this. And now in phases, only the pure sinusoidal induced EMF remains. So the output from the neutral connected star connection is sinusoidal. And the other advantage of star-star connection is that we know that in star, line voltage is equal to √3 times phase voltage, and line current is equal to phase current. As the current relation in star connection is line current is equal to phase current, means in phases high current will flow. So because of which high cross section conductors are to be used in star connection, means less number of turns in each phase, means less insulation is required. So these are the advantages of star-star connection. Now let's move on to the disadvantages of star-star connection. The main disadvantage of star-star connection is neutral shift, means there is oscillating neutral in star-star connection, and to reduce that, neutral connection is taken. And the second disadvantage is non-sinusoidal output. So as there is no neutral connection, the output from star connection is non-sinusoidal. So there is harmonics issue. And the third disadvantage is over voltages at light loads and voltage drops at unbalanced load. So these are the disadvantages of star-star connection. And the application for star-star connection is, this connection is economical for small large voltage transformers, and because of these disadvantages it is rarely used for unbalanced loads. So this is about star-star connection.